Hello everyone. Today I'm going to continue discussion about singularity points of analytic complex variable functions and how to determine their types. Let me remind you the very first page from our previous tutorial. I need to adjust my camera a little bit, sorry. Okay. So we were discussing in tutorial 12 part 1, I mean. So in that tutorial, we discussed singularities. What is the singularity of the function? Let me remind you. This is the point where our function doesn't make sense, where its domain sort of breaks. So for example, if you look at this function, you can see that it looks like a fraction. And you know, a fraction means division operation, and it's never allowed to divide by 0. That is why z is equal to 0 is the singularity point for this function. The same reasoning could be applied to this fraction, to this function. You can see that this denominator turns into 0 when z is equal to 3. This means that 3 is the point of singularity for our function. And the problem here in complex variable theory is that you need to determine the type of singularity and calculate the residue of the function in this point of singularity. How it can be done? Last time in the previous tutorial, I outlined you, you know, the layout. How are we going to explore this topic? So the first method was the most general one. If you manage to expand your function into Laurent series, this is the best method actually, because you can immediately see both things. You can immediately see the type of singularity, and you can immediately see a residue of this function in this point. So this is the best method, the perfect in every respect. But unfortunately, it's not always possible to find the expansion of the function into Laurent series. Sometimes it's so difficult that it seems almost impossible. That is why it's good to know some shortcuts, even though in some situations they are not so short, but nevertheless they are called shortcuts. So as I outlined before, as you can see from this schematic, there are even two methods which allow you to avoid expansion into expanding your function into Laurent series. So this particular tutorial will be devoted to method 2. Method 2. I think it should be quite enough for one tutorial, for one video. Okay, so what does this method mean? So let's write down method 2. Method 2. Method 2. And what is this method about? I want to highlight you from the very beginning. Let's write like a note. Unfortunately, this method only allows you to deal with poles. You probably remember that there are three types of singularities. Removable singularities, poles of some order m, and essential singularities. So this particular method, unfortunately, it has some limitations. It only allows you, let's write down this very important idea. It only allows you to deal with poles, unfortunately, only to deal with poles of any order. So it means that method 2 is limited. Method 2 is nice. I would call it nice, but limited. Nice, but limited. But you know what? On the other hand, poles are the most popular types of singularities. So there is a chance that you may come across poles in your exam test. I think so, because they are the most popular singularities. If you look for your study guide, you will immediately see this, immediately realize it. So okay, so how does it go? What does this method consist? It turns out that if two conditions are true, first, your function has a special structure. So it looks like a fraction, phi of z divided by z minus 0 to the power of m. This is the first requirement. And second, phi of z0, that is a nominator of this function, is neither equal to 0 or infinity. So if these two requirements are true, are correct, then it means that Z0 is a pole of order m, So as you can see, so this is the first statement and this is the second statement. So it looks like theorem. So as you can see, it does seem like a very nice way of determining the pole and the order of the pole without expanding your function into Lorentz series. But it should satisfy these two requirements. In the first place, it should look like a fraction. And of course, you looking at this fraction, you immediately realize, yeah, Z0 is the singularity points, because if you substitute Z0 instead of Z here, you will get division by 0, which is not allowed, but which is at the same time means that Z0 is the singularity point. So if your function looks like this, but what does the second requirement mean? It means that if you substitute your singularity point Z0 to the nominator of this fraction, you will not get no 0, no infinity. It will be some just nice number, non-zero number. That's it. So, but what about residue? What about the residue? What is the shortcut for the residue then? Because before that, we were calculating residue. We didn't even calculate the residue. We just looked at the expansion to Lorentz series, and we were looking for this coefficient. Do you remember? C minus 1. So this was equal to residue. But now we decided not to do it, or maybe it was too difficult for us. What is the other way? The other way is to use this formula, which maybe wouldn't look very, friendly to you at first glance. So residue, but let's write it down anyway because it's super popular formula, super famous and so on. So the formula goes like this: 1 divided by m minus 1 factorial times limit when z tends to z0. Z0 is our singularity point, and here you will have to calculate derivative of the mth order. So our formula gets bigger and bigger, as you can see. As I said, at first glance, it doesn't look very attractive. So f of z times z minus z0 times m, and that's it. Maybe it's a good idea to put a frame around this formula. So formula looks sort of a little bit huge, but that's okay. Everyone gets used to it very quickly. So, but you know what? We can, if you analyze this expression here in these brackets and this function, you realize that, oh, this is actually what is written here. It's actually equal to nominator of this fraction, phi of z. So I could have written this formula in a nicer and shorter way. Why didn't I do this? I did it deliberately, because because this formula will be, we are going to use this formula for method 3 as well, and in this case, in method 3, it will look just like this. There won't be any phi of z in method 3, and that is why if I chose to write you phi of z here, you might have got under the impression that you need to learn two formulas. That is why I decided to give up this idea and write you the general formula from the very beginning. I think this is the best way. You can realize that this is phi of z, or maybe you can't. It doesn't matter. It's better to get used to the formula in this way, in this form. Okay, so let's try and practice applying this formula. So we can actually go over the same examples as last time. So I'm going to take examples from the last tutorial, from our tutorial sheet, because it's always interesting, even though we already solved these problems. But I think it's always interesting to solve the same problems using different methods. It's then considered to be more useful. Okay, so what is our function? The first function will be z plus 1 divided by z squared. I think we solved this problem last time. So you can, if you are curious, you can watch the previous tutorial once again and just compare these two solutions. But now, of course, I'm going to concentrate only on this function, on this method. We're discussing method 2. So you immediately spotted the fraction, and you immediately think, what if I it means that what if I try and imagine my function being in this form? It would be very, very nice. So you're comparing your function with the first requirement. Your function should look like this. Let's try and do this. So it's pretty obvious that phi of z will be the denominator of our function. So phi of z is equal to z plus 1, of course, no doubt. What about z0? Z0 will be, in our case, it looks, we have z squared here, and here we have z minus z0 to the power of n. You can easily imagine that this z could be rewritten as z minus 0. So our z0 is equal to 0, and our m is equal to 2, of course. Okay, so we managed to discover that our function does look like this theorem says. But what about the second requirement? The second requirement is an absolute must. We need to check that nominator doesn't turn into something ugly. Okay, so let's check our phi of z0, which is 5 of 0. And 5 is z plus 1. I can rewrite it like this, maybe. Some people, some mathematicians prefer to write like this. So it will be 0 plus 1, it's 1. Look at this. It's not 0 and it's not infinity. This is just a nice number 1. So we are very lucky. It turns out that the requirements of our theorem are both met, and we can make this conclusion. So our z0, which is 0, is the pole of order 2. So look at this, how quickly we managed to do it. So pole of order 2, that's it, of order m is equal to 2. So we managed to cope with the first task relatively easy. But now, of course, we need to apply this formula. This formula, we know that our m is equal to 2, so we need to start applying our data into this formula. So I'm trying to hold it in the screen. So let's start. Residue of f of z in point 0, of course, in our case. So what we will have here, m is equal to 2. 2 minus 1 will be 1. 1 factorial is just 1. I'm sort of lazy to write it. Let's better move to the limit. So limit when z tends to 0, of course. And what is the order of the derivative will be here? M minus 1 will be 1. So it means just the first derivative, which is d over dz. You don't need to write a 1 here, of course, in this case. And as we discussed before, the whole expression inside the brackets is actually equal to phi of z for any situation. What is our phi of z? It's just z plus 1. So you know what? When you plugged in your own data, to this formula, it doesn't look so terrifying anymore. So all we need to do, we need to differentiate this function, which is super easy, of course. The derivative of this function is just 1, and limit of constant is the same constant. So residue is 1. So that's it. So residue of our function is equal to 1, and the type of singularity is pole of order 2. So as you can see, in some cases, in some beautiful cases, this task can be solved relatively quickly. So we didn't have any problem solving this task at all. Okay, let's move to another example. We need at least 2 or 3 examples. No, the second example is quite a long one, but I did it deliberately because you still can practice your own skills on your own. And my task is only to give you direction. So the second, I'm running out of green, I'm afraid. It's better to use red now. So example 2 will be the function. I don't think we solved it in the last time because we are going to discuss this function. So in the denominator, you have z minus 3 times z plus 5. I don't know, is it squared or not? I can't make out my own handwriting. Oh my gosh, I think it's squared. Yeah, it's squared. So I don't think we have dealt with this function at any point because it looks pretty terrifying if you imagine trying to expand it into Laurent series. Of course, it sounds too daunting. Of course, you still can do it, but it involves a lot of transformations. It's better to use our new method. But you know what? The problem is that we can see 2 singularity points here. How can you approach this task? And that's the reason why I decided to explain you this example, because it's very interesting actually. Very curious to see how you can apply this formula to the function which seemingly doesn't look like it should, according to the theorem. Okay, so let's write it down. So we spotted 2 singularity points. 2 singularity points. 2 singularity points. Z1 is 3, because that's when this expression turns into 0, and z2 is equal to minus 5. And we need to deal with these 2 points separately, one by one. So let's start with z1 is equal to 3. This is our first singularity point. So, according to our theorem, according to our method, we need to see this structure in the function. It does look like a fraction, of course, our function, but not quite this fraction, seemingly. But you know what I'm going to do? I'm going to do some beautiful trick. First of all, I'm going to just to copy my function first. Z minus 3, z plus 5 squared. But you know what I'm going to do? I'm going to rewrite it in a little bit different way. I'm going to uh, take these two guys together, the whole expression, and put it into numerator. I'm running out of space, so I'm going to the next line. So z plus 8 divided by this guy, z plus 5 squared, will be my nominator. And the denominator becomes very small, just z minus 3. But you know what? Why I did it? What was the purpose of doing so? Because this guy will play the role of phi of z in my case, and this guy will be z minus z0. So I can rewrite it in a general form. I can compare it with my theorem. So phi of z divided by z minus z0 to the power of m. You remember this template from our theorem. So what do we have here? Now we can easily compare our function. We are dealing with a point z, so z0 is 3, is our singularity point, of course. And this expression is in the power of m, so it means that m is equal to 1. But you know, maybe, so it looks like it's going to be the pole of order 1. But you know, it was too early to make any conclusions because I haven't checked the second requirement. Let's do it. So what do we need to do? We need to check that phi of z0, which is in our case phi of 3, is not equal to something bad like 0 or infinity. So let me rewrite function here, phi. Function phi looks like this. And so I put z is equal to 3 here. It looks much more convenient to write it like this. Okay, so let's plug it in. So 3 plus 8 will be 11. And what I have here, 3 plus 5 will be 8. 8 squared is 64. Oh, look at this. It's not 0 and it's not infinity. So our conclusion was quite right. So this guy, it is the pole of order 1. Pole of order 1. Of order 1. So our first. So look at this. I used a very interesting trick. I organized my function. I rewrote my function in a little bit different way, in a way which is more convenient for me to compare this function with the template given in the theory. So it's not necessary to put up with the fact that your denominator looks like this. You can play around with it. You know, you can restructure your function according to your needs. So this is a very interesting trick. But you know what? It's not the end to the story, because now we need to calculate residue in this point, in this simple pole. Okay, let's do it. And first of all, I probably need to copy this formula. Because I need to keep it on the screen all the time. Okay, let's recall this formula. So residue of some function f of z in the point z0 is generally equal to 1 divided by m minus 1 factorial dm minus 1 dz m minus 1. It denotes the order of or derivative of order m minus 1, of course. And here in parentheses, we actually have this phi of z. Phi of z. I'm trying to, I'm a little bit lazy this time, so I'm trying to write just phi of z. Let's plug in our data, our information. What do we know about our pole? Our pole is order of 1, so m is equal to 1, and here you have 0 factorial. I hope you are not confused with 0 factorial. It's considered to be 1 in mathematics. Maybe you already know it, maybe not, but just... So it means that I don't need to write anything here, it's just 1. What about the order of derivative? So m is equal to 1. It means that it will be 0. What is the derivative of order 0? It means no derivative at all. Oh, nice news. So all we need to do... Oh, I forgot to write the limit here. Too bad. Limit when z tends to 0. Z0. Sorry for this mess, but... okay, what can you do? Okay, I can write it here after all. So limit when z is equal to what? To 3 in our case. And no derivative at all. Derivative of order 0, as I said before, it just means that no derivative at all. So all we need to do, we need to write phi of z here. Where's our phi of z? Phi of z was in the previous page. Move it here. Here it was. Z plus 8 divided by z plus 5 squared. And now we can plug in 3 already. But I have an impression that I already did it before. Yeah, we already did before. So it was 11 over 64. So we have our first result. So the first singularity of this function, let me remind you of the function. So we are dealing with this function at the moment. We discovered that it has two singularities. We already explored the first one. Z1 is equal to 3, turned out to be pole of order 1, or simple pole, as people prefer to say, and the residue is equal to 11 over 65. Okay, now it's time to explore the second singularity, which was Z2 is equal to minus 5. Again, let me copy the function here first. So our function f of z is z plus 8 divided by z minus 3 times z plus 5 squared. So I think that you know exactly what I'm going to do now. I'm going to reorganize my function in a different way, because I'm interested in this expression, which is responsible for this point minus 5. And that is why all the rest of this expression could be viewed as phi of z. I can move it to the denominator of this fraction. So let me write it in this way. So this expression will be on top. It will be denominator, z minus 3, and this guy, z plus 5 squared, will be left in the denominator. So it looks like this guy is going to play the role of phi of z in the. So as you can see, I'm playing around with the same function, and every time the role of phi of z goes to a different expression, because I'm adjusting my function to be suitable to my needs, to my current needs. So now my need is to deal with minus 5. That's why I'm interested to have the expression responsible for minus 5 in denominator, and all the rest should be phi of z. Okay, let me rewrite the general template from the theorem again, so that it would be more important, more convenient for us to compare. So what do we have now? Of course, as before, we can write that z0 is minus 5, of course, it's pretty obvious. M is equal to 2. So it looks like this singularity, minus 5, is going to be pole of order 2. But, you should be cautious, because you should remember that the theorem consists of two requirements. We already only checked the first requirement, but the second requirement is still there, is still to come. So let's check it. So our 5 of z0, which is actually phi, is here. Oh, sorry, sliding out of view. So our phi is here, z plus 8 divided by z minus 3. And we need to plug in minus 5 instead of z0. Okay, minus 5 plus 8 will be 3. And here we have minus 8. So it's definitely not 0 and not infinity. That is why our conclusion was true. So our singularity point minus 5, it is a pole of order 2. So our suspicion is confirmed, has been confirmed. But now we need to calculate the residue of our function in this pole. Okay, let's move to the second page. So again, maybe it's better for me. I'm sort of lazy to rewrite this formula all the time. Maybe I should place it just somewhere like this. So this is the formula for calculating the residue in the pole of order m. Note that this formula is only true for poles, unfortunately. As I said, the whole method too only works for poles of order m. But nevertheless, it's quite a nice method. And moreover, poles, as I said, are quite frequent in this problem, so no problem. So, okay, so what is our data? Our data is that our z0 is minus 5, and m is equal to 2. The order of that pole turned out to be 2. So we can plug in our data to this formula. So residue of our function f of z at the point minus 5 is equal to what? So this guy again will be 1 because 2 minus 1 will be 1. 1 factorial is 1, so I'm not going to write this 1 here. Okay, something blurry. Okay, I'm going to write this limit. Limit when z tends to minus 5. And what is the order of our derivative? 1. So it's just the first derivative, d over dz. D over dz. And here we need to plug in phi of z. What is phi of z in our situation? I seem to have lost it. Ah, yeah, here it was. It's the fraction z plus 8. Let me rewrite it for you. Z plus 8 divided by z minus 3. So it's not a terribly challenging task, of course, to differentiate the fraction. You know this, what is it called? A quotient rule, of course. So let's do it. So I'm rewriting limit in front. Z is tends to minus 5. And now I'm going to take the derivative of this fraction. So I'm going to do it a little bit more detailed than usual. Just to remind you this quotient rule. So it will be minus this guy and denominator prime. And denominator should be squared. So I did it in very much detail. Okay, so what do we have here? This is of course 1. 1 times z minus 3 will be z minus 3, of course. And the derivative of this expression is 1 as well. So it doesn't matter. Minus z minus 8 z minus 3 squared. And of course it needs a little bit of simplification. So these guys will cancel out. And finally, we are left with minus 3 minus 8 will be minus 11 and z minus 3 squared. And now all we need to do, we need to plug in minus 5. We need to calculate this limit, but the limit is super simple. We don't need to know to apply some special tricks. We just need to plug in minus 5 instead of z. That's it. So minus 11, what is going to be? It will be 64 again. Just almost the same result, but with a negative sign in front. So that's it. That's it. As you can see, the example number 2 was quite funny, quite interesting. And so you know how you can apply this method, nice method too, even in the situations which doesn't seem suitable for this method at all, seemingly at first glance. But then you realize that you just need to know some tricks. Okay, so the question arises that I'm sort of promoting you method 2, and you might get under the impression, oh, it's so nice. Why did we bother learning this expansion tolerance series at all? But you know what? It turns out that nothing in this life is perfect, including all these beautiful theorems of mathematics. Method 2 is simply not perfect. It's not, unfortunately, it cannot be applied to just any situation. And now I'm giving you examples. So why is method 2 not perfect? Let's give it such a title. Why is method 2 not perfect? Why can't we apply it anywhere? Because it's so good, seemingly so simple. I'm just going to convince you by 2 examples. So let's have a look at the first example. So let's consider function f of z divided by sinus hyperbolic of z divided by z. You might say that, oh, this function has such a nice structure. It does look like fraction. Let's try and compare it with our template, with our favorite template. And you might say that you've already done almost 3 examples, and every time we were successful. We managed to see that our function did satisfy the requirements of this beautiful theorem. But you know what? Look at this. Yes, this function does have this structure. But what about phi of z? The role of phi of z goes to sine. And I didn't say that singularity point is of course 0. Of course, you immediately spotted this. So z minus 0, and it seems like it's going to be the pole of order 1 probably. But wait a little bit. We haven't checked the second requirement of our favorite theorem. Let's check it. So our phi, of course, is this function, hyperbolic sinus of z. And what do we need to check? We need to check that phi of z0 is not equal either 0 or infinity. In our case, it will be phi of 0, which is sinus hyperbolic of 0. But you know what? The bad news is it is equal to 0. So What does it mean? It means that our theorem doesn't work, unfortunately. Only if both requirements are met for your function, only in this case, you can apply the first, your theorem, method 2, and make a conclusion that this guy, z is equal to 0, is the pole of order 1. But in our case, no. Requirement number 2 is broken. So you can't say anything about this singularity point. So this is one example where you can't apply method 2. So unfortunately, it's not perfect. Another example, maybe even, yeah, a little bit different situation. Look at this. So this situation, what's wrong with this situation? You can see it at first immediately, because this function simply doesn't look like it should in this theorem. Look at this, phi of z, it should look like a fraction with a very explicit denominator. It doesn't look like fraction at all, and there's no way to transform it into fraction, so it cannot be applied. You definitely need some other method. By the way, in both cases, in both of these examples, the best way is to expand it into Laurent series, and it's not difficult at all. And I think that we did these both examples in our previous tutorials. But of course, there will be even more examples when you can't even apply method 1, method 2, and that is why we will need method 3 as well. But it's not going to be in this tutorial. It will be the topic of the next tutorial. And as for homework, I think it would be very useful for you and very curious to do the same homework which I gave you at the end of last tutorial, the same 7 problems. I think it would be pretty curious and interesting for you to go over the same, absolutely the same problems, but trying to solve them with a different way, trying to apply this method too. In some cases, maybe you won't be able at all to apply them. I think that there are like I can see two cases only out of 7 when it's not possible to apply method 2, but I'm not going to tell you them. You're supposed to determine it yourself. So my only hint that out of these 7 problems, only 2 uh, are impossible to be solved by method 2. But as for others 5, that's okay. And just for your convenience, I'm giving you the answers as well for all the problems. So remember, only 2 of these 7 problems are unsolvable by method 2, but the remaining 5 could be easily solved and very beautifully. Okay, so that's it. In our next tutorial, we are going to discuss method 3.